Let us now see how the temperature of radiation in the universe evolves as it expands. And with whatever we have learned till now, we can do a simple calculation to understand this. As before, the continuity equation of radiation with P equal to rho by 3 will give us the density of radiation going as the inverse power a power 4. Now we know that if we have a black body radiation, then the total energy density in that radiation goes as the fourth power of the temperature. Now there are reasons to believe, and now observations to confirm it, that this radiation is a black body spectrum in our universe. So if we take these two equations, we immediately get that the temperature of radiation goes inversely with the scale factor. In other words, as the universe expands, the temperature of radiation drops. Further, we also saw that when we have pressureless matter, then the scale factor A goes as T to the power 2 by 3. If we have pure radiation, then this scale factor goes as T to the power half. In general, for most kind of materials which we are familiar with, this scale factor will go as T power n with n less than 1 but greater than 0. So these two equations imply that the temperature of radiation in the universe goes as T to the power minus n, and what it implies is the following. Since n, as I said, is greater than 0, earlier the time we go, that is closer we go to the beginning of the universe, that is if T decreases, the temperature of radiation increases. It means that the earlier the epoch I am looking at, the hotter the radiation in the universe was. In particular, if suppose we go arbitrarily close to the beginning of the universe, that is when T tends to 0, the temperature goes to infinity. And this is what is usually called the Big Bang. In other words, the universe started with an infinite temperature and kept cooling as it expanded. Now the photon temperature is very high in early universe, and as we will see in the next slide, this has important implications for the study of early universe. Why is it that in the study of early universe, what kind of physics can this study of early universe give regarding the phenomena in high energy physics? As I said, in early universe, the temperature was very high. Now, if suppose you have radiation which is at a high temperature and it is interacting with matter in the universe, then matter and radiation will be in equilibrium. In other words, it will be a common temperature shared between matter as well as radiation, and so the matter will also be at a high temperature. In other words, particles which constitute the matter will be whizzing past each other with very high velocity. It means that when they collide and scatter, then these collisions will be high energy collisions. Then these will be similar to the high energy collisions of particles which are done in high energy physics experiments in various places, different places in the world. And so what one expects is that the results of the high energy collisions which are being studied in various laboratories, they would have been replicated in the early universe because of a natural reason why they are going and why they are colliding at high temperature. In other words, the early universe phase is called a poor man's high energy physics laboratory. That is, corresponding to every high energy process in the lab, we expect at an early enough time such a process should be active in the context of cosmology. So now this, let me just read out. See, here I have just given some numbers as to, if I go at earlier times, how hot the universe is. For example, if suppose I consider the universe to be when it was about 9 billion years old. Today the universe is roughly about 13 to 15 billion years old. So when it was 9 billion years old, the temperature of radiation was about 6 Kelvin. Today it is about 2.73 Kelvin. When it was about 100 million years ago, it was 30 Kelvin. But if I go to something like the universe was 10 to the power minus 12 seconds, the temperature of the universe was as high as 10 to the power 15 Kelvin. And if we go to what we call the Planck time, that is the earliest time where we have any idea of what could have happened in the universe, the time corresponding to that epoch is about 10 to the power minus 43 seconds, and the temperature is around 10 to the power 32 Kelvin. So, as I said, as we go to higher temperature, we are looking at situations where particles are colliding at higher and higher energies. Hence, we expect that high energy physics experiments which have been done or which are theoretically speculated would have actually happened in the universe at early enough times.